Hello, everyone, and welcome to part 3 of the lecture video on alkene addition reaction. Okay, as I mentioned, we're going to be continuing to talk about addition reactions of alkenes. I am using slides from the 3rd edition of David Klein's Organic Chemistry, which is why it says chapter 8. If you're using edition 1 or 2, it would be chapter 9. Okay, so just as a review of where we were and where we're going. So in parts 1 and 2, we've covered the first 5 reactions. And then in part 3, we're going to cover the last 5 reactions. So starting from bromination/chlorination, sometimes that's just called halogenation, to halohydrogen formation, both anti and syn dihydroxylation, and lastly, ozonolysis. Okay, starting us off with halogenation. Halogenation is the addition of 2 halogen atoms across a carbon-carbon double bond. So there is no issue of regioselectivity with halogenation since both carbons are getting the same atom. For example, if you use ethylene and treat it with chlorine gas, you will get 1,2-dichloroethane in great yield. Halogenation is actually a key step in the production of PVC, which stands for polyvinyl chloride. So you can see that the reaction that we see here is the first step in the formation of PVC. We do an elimination of one of the halogens to get vinyl chloride, and then use vinyl chloride in a polymeric addition reaction to get PVC, which is used in plumbing and things like that. Okay, so halogenation is actually only really practical with either chlorine gas or liquid bromine. And that's because with iodine, it's just too slow, and with chlorine, the reaction is too exothermic and difficult to work with. The stereoselectivity, because even though there isn't an issue of regioselectivity, we still need to think about stereoselectivity, is that halogenation occurs with anti-addition, meaning that the 2 halogens get added on opposite sides of the pi bond. If there are 2 stereocenters formed, you would get a racemic mixture, but both products would be from anti-addition, which means put 1 bromine on a wedge and 1 bromine on a dash. So how does this reaction work? Bromine and chlorine are nonpolar because it's not considered a polar bond when you have 2 of the same atom attached to each other with the same electronegativity. But even though bromine is nonpolar, it's what's called polarizable, which means that if you have approach of an electron-rich nucleophile, it will induce a dipole. So the electron-rich nucleophile, when it approaches bromine, will cause a lot of the electron density in bromine to move to the other side of the molecule so that there is opposite charges that can attract. And this happens pretty well with chlorine and bromine because they're large atoms. So their electrons, particularly the valence electrons, are held further away from the nucleus. So they have less attraction to the nucleus, and they have more freedom as a result. So they are what we call more polarizable. So if one of these bromines can take on a delta positive, it can be electrophilic. So then the pi bond, which we know is nucleophilic, right, can attack the electrophilic bromine, causing a loss of a leaving group. So this is a nucleophilic attack arrow followed, and at the same time, loss of a leaving group. So you can kind of think of it as like an SN2 reaction, generating this intermediate, which appears to have a carbocation. Let's take a little bit closer look at this reaction mechanism. So if it occurred the way we saw in the previous slide, then we would actually expect to get both syn addition and anti-addition products. Because if we have a true carbocation with an empty p orbital, then the bromide, which does a nucleophilic attack after the first step, can add to either side of the planar positive carbocation with equal probability, leading to both syn addition and anti-addition products. But what we see when we look at the stereochemistry of the products in reactions that we actually try in the lab, is we see that we're only getting anti-addition products, right? So this mechanism is not consistent with the observed products because we are not seeing syn addition products. So it is likely that we're not going through a true carbocation intermediate. So what could happen instead of forming a true carbocation intermediate? Well, we could get the formation of a bromonium ion intermediate. It would be consistent with anti-addition. So in that first step where we showed nucleophilic attack and loss of a leading group, if one of the other lone pairs on the bromine that got attacked reacts with the empty p orbital, right, the positive charge that's developing on this carbon, then we end up with a 3-membered ring where both carbons are bonded to bromine and the bromine has some positive charge. Now, there are multiple reasons why this intermediate would be reactive. First of all, bromine with a positive charge is not very stable, as well as the fact that there's a 3-membered ring. So the intermediate is very electrophilic and electron deficient. So it's set up really well to be able to be attacked by the bromide, which was formed in the first step through loss of a leaving group, to act as a nucleophile and do a nucleophilic attack. You might think it would attack the bromine directly, since the bromine is the one with the positive charge. However, it will actually attack one of the carbons attached to the bromine, such that the electrons in the carbon-bromine bond will then get delivered to the bromine as a lone pair, satisfying it so that it no longer has positive charge. So it's actually the carbons attached to the bromine which are getting attacked by the nucleophile, not the bromine itself. So this occurs through an SN2-like mechanism with inversion of stereochemical information at this carbon, resulting in the anti-stereoselectivity. So let's look at what this would look like if we started with a acyclic alkene instead of a cyclic alkene. So if we start with an acyclic alkene, then it's common to have trans double bonds as well as cis double bonds, whereas with small rings, they can only accommodate a cis double bond. So let's look at each of these individually. Starting from cis-2-butene, if we add bromine, recall that this undergoes anti-addition. So if we're forming 2 stereocenters, then we need to make sure to show the relative orientation of the groups correctly. So in this particular slide, they're showing products drawn through model 2. And remember, we've been talking about using 2 different models to draw products in the activities. So if you're following along with your learning from the activities, this would be a way of drawing them using model 2, where the incoming groups get placed on either a dash or a wedge. Because it's anti-addition, we're going to place one on a wedge and one on a dash, knowing that we can get a racemic mixture if this indeed is a chiral compound. And since there's no internal plane of symmetry, with 2 chiral centers, this will be chiral, and you'll form a mixture of enantiomers. With trans-2-butene and anti-addition, we end up with a meso product. So that means that it does not have an enantiomer because it's achiral. The way to see that is through actually rotating the central carbon-carbon bond so that the 2 bromines are on opposite sides of a plane, and we can see that there's an internal plane of symmetry. So recall that just because it's drawn one particular way, whenever you have reduced this double bond to a single bond, now we have free rotation about single bonds. We can rotate this and observe the molecule in a different way. All right, let's go ahead and do a practice problem and predict the major products. So recall, if you don't form any stereocenters, you don't need to worry about stereoselectivity. If you form one stereocenter, you'll always get a racemic mixture. And if you form two, you need to think about whether or not the reaction is syn selective, anti-selective, or not selective at all, which would give a mixture of base. Bromination is anti-selective. So we want to remember that when drawing products. When you're drawing two stereocenters, you can either use model 1 or model 2, which was described to you in the worksheets, to draw products. And so when I go through it, I'll do it both ways, so that you can see the answer with whichever way you have chosen as your favorite way of drawing products, given the option. But with cyclic alkenes, it's more common to use model 2 to draw products. So go ahead and practice this, and we'll go over it. All right, so I am going to assume you've worked on this, and we will go over it. So we are going to be adding bromine across the double bond. Both carbons will get a bromine. This one will not end up being a stereocenter because of the two hydrogens attached here, but this one will. So we'll end up with a product with only one stereocenter, in which case we want to make sure we indicate a racemic mixture. So we can draw one of the two enantiomers. You don't need to indicate that this is on a wedge, again, because this is not a chiral center. All right, let's look at this one. If we add a bromine on both carbons of the alkene, we'll actually end up with two different stereocenters. So here's where we really need to pay attention to that anti-stereoselectivity. So there's two different models, right, that are described in your activity. So two different ways of potentially approaching how to draw the product here. So I'll use how to draw the product using model 1, followed by model 2. So with model 1, we're going to place the two incoming groups in the same plane using a regular line indicating the bonds. And then we're going to look over here and see what's attached to each sp2 hybridized carbon. Here we have a hydrogen going this direction and a methyl coming here. So if we're just looking at it, we'll just draw the hydrogen back and the methyl coming out of here from the way it's drawn here. And then, because again, this is undergoing anti-addition, right, we need to make sure to switch these two groups when we're drawing it using this model. So that means the methyl here will go back and the ethyl group will come forward, right? And this would be plus the enantiomer. Right, so this is model 1. Again, the models are described really well in your activities. And then next we can do model 2. For model 2, I draw the carbon scaffold, the longest carbon scaffold, just as it looks. So this would be like a pentane. So we'll start there. And then I want to make sure to add the two bromines anti. So one will be on a wedge, one will be on a dash. And it doesn't matter which you choose, as long as you write plus enantiomer. Let's say we put this one on a wedge. That would mean that the bromine over here would go on a dash, which would shift the methyl here forward. So we place it on a wedge. Right, so this is how we would draw the same product. These are equivalent, right? Just drawn a different way. And if you're following along your activity, this would be how I would do it using model 2. Okay, moving on here to the last one. So remember I said it's really common to use model 2 when you're starting with a cyclic substrate. And that's just because that allows us to leave the ring in the plane, which is a little bit easier to draw. So I just draw a 5-membered ring, and I want to make sure again that those bromines are in. So if I put one up, that means that the other one must go back. You would also get an anti marker. Right, moving back to the slide. Let's move on to the halohydrin formation reaction. So halohydrins are formed when halogenation is conducted in water. Water will actually act as the nucleophile that attacks the bromonium ion instead of bromide. So you can see the same bromonium ion is formed that we formed in halogenation. Water is doing a nucleophilic attack. It's an SN2-like reaction, and therefore we get the anti-addition product, just like with halogenation. But when water does the nucleophilic attack, it forms an oxonium ion, which is charged. In order to have a stable enough product to isolate, it needs to be neutral. So we'll draw in another water molecule that can act as a base to deprotonate it to get the final product, which is the anti-halohydrin. Remember that we can do halogenation with bromine or chlorine. So we can form a bromohydrin or a chlorohydrin this process. Okay, so halohydrin formation is a regioselective process. Remember that when we're adding groups that are not identical across the double bond, we need to consider regioselectivity. With halogenation, it was the same halogen, either 2 chlorines or 2 bromines. So we didn't worry about regioselectivity. Now we need to consider it because we're adding a halogen, either chlorine or bromine, and an OH group. Well, it turns out that the OH group gets added to the more substituted carbon, and the halide gets added to the less substituted carbon. I would not consider this to be Markovnikov or anti-Markovnikov regioselectivity, because Markovnikov's rule states that a hydrogen atom is likely to get added to the carbon with more hydrogen atoms. And in this case, you can see we're not adding a hydrogen atom. This is a reaction that where both groups are non-hydrogens, right? So we really wouldn't consider it Markovnikov or anti-Markovnikov. We just want to remember, though, that the OH gets added to the more substituted carbon selectively. Okay, so again, the bromonium ion gets formed, and then water does a nucleophilic attack. But notice here that it's doing a nucleophilic attack at the more substituted carbon through an SN2-like process. This should be sort of strange to you, right? If you're thinking about your knowledge of SN2, right? SN2 reactions occur at less substituted carbons, like primary alkyl halides and methyl alkyl halides. And they don't really occur at tertiary carbons like we're seeing here. This is a bit of a strange thing, and it will explain why it attacks the more substituted carbon on the next slide. But for now, after that SN2-like nucleophilic attack, which leaves us with the bromine and the eventual OH group on opposite sides, then another water molecule will deprotonate to give us the halohydrin. So why does it attack the more substituted side via an SN2-like backside attack process occurring through inversion of stereochemistry? So you might have noticed I've been saying SN2-like and not SN2. So that's very different. This is actually a mechanism that is somewhere between SN1 and SN2. So I know previously we talked about those two mechanisms like they're exclusive things, right? Something either undergoes SN2 mechanism or it undergoes an SN1 mechanism. But there is such a thing as somewhere in between. And the reason for that, the reason I say that is because we are seeing inversion of stereochemistry leading to the anti-product, just like SN2 would predict, but it is the nucleophilic attack is happening at tertiary carbons. It's happening at the more substituted carbon, which would be more similar to SN1, where the nucleophile gets attached to the more substituted carbon. So what's going on here? Well, it turns out that the nucleophilic attack and loss of a leaving group that you're seeing here are not occurring in like a 50-50 amount. So they're not occurring exactly perfectly simultaneously, the way that these arrows are implying, the way that an SN2 reaction typically works. Instead, what's happening is the carbon-bromine bond is weakening at a faster rate than the incoming oxygen-carbon bond is being formed. So this is actually already starting to weaken, leading to a sharing of the positive charge, right? If this bond starts to weaken, then the electrons get shifted to the bromine, and there's less positive charge on the bromine, and the carbon starts to take on some of that positive charge. You can think of it as positive charge sharing, right? If these electrons get added to the bromine as a third lone pair, then it starts to have a partial positive charge instead of a full positive charge, and the carbon starts to take on a partial positive charge. That then creates an electrophilic center that attracts the nucleophilic oxygen, and we start to form the oxygen-carbon bond. So essentially, this bond, even though it appears to be a regular bond, it's significantly weakened, leaving partial positive character on this carbon that's attracting the nucleophile. That's not occurring on the other side to the same extent. And if you think of this as taking on a partial positive charge, then it's not really tetrahedral anymore. This carbon becomes somewhere between a tetrahedron and a trigonal planar geometry, right? Where there's some influence of the bromine forming a bond, but not completely. So this tetrahedron sort of opens up. If the leaving group starts to leave, then the tetrahedron is allowed to, leaving group is leaving, the tetrahedron is allowed to open up a little bit, like opening up the umbrella, allowing for a nucleophile to be able to get in to do backside attack. So in essence, what I'm trying to say is the more substituted carbon has more cationic character, that it's not a true tetrahedron where it would be difficult for a nucleophile to get in and do backside attack. Instead, it's almost trigonal planar, right? And that leaves room for the water to come in and attack that carbon. So it's somewhere between SN2 and SN1. Okay, let's do a practice problem when it says predict the major products. So again, let's go over what we want to do for this problem. First, ask yourself, given the reagents, bromine and water, what's getting added across the double bond, right? Your answer should be bromine and OH. And then because it's not the same group, what's the regioselectivity, right? So you want to remember that that OH group should go on the more substituted carbon, placing the bromine on the less substituted carbon. Then we want to think about stereoselectivity. Again, if you're not forming any stereocenters, we don't have to consider stereoselectivity. If you're forming one, it's always formed as a racemic mixture. If you're forming two, we want to remember that halohydrin formation is an anti-selective process. So we need to make sure that the bromine and the OH are getting added from opposite sides of the pi bond. So very similar to halogenation. The difference is that replace that bromine on the more substituted carbon with an OH, and you'll be able to draw the products very easily. Okay, let's go ahead and practice. So predict the major products. So again, you really have to think of bromination, where the more substituted carbon instead gets an OH instead of a bromine. And the less substituted carbon gets the bromine. That is not going to become a chiral center. And the more substituted one will get an OH. That will become a chiral center. We will get a mixture of enantiomers. In this case, we're forming two new stereocenters. So recall that the OH group will get added to the more substituted carbon, bromine the less substituted carbon in an anti-selective process. So we can use either model 1 or model 2 to draw those products. So if we're using model 1, then we will draw our bromine, which is attached to the less substituted carbon. And then on the right here, I'm having my more substituted carbon, which will get an OH group. Then I can add in these groups. So this is a methyl coming out at me, and a hydrogen pointing back, which you can either draw in or not draw in. Since this is anti-selective, then we want to switch these two groups. So the methyl will go back, and the ethyl group will come forward. Right? This is plus the enantiomer. That's using model 1. Model 2, we'll keep the pentene in the plane. We're going to make sure to add the bromine here, the less substituted carbon. If I place that on a wedge, then I want to make sure that my OH group goes on a dash, which move this methyl group forward on a wedge. Okay, so this also produces a mixture of enantiomers. And again, this is the same product, just drawn two different ways. Model 1, right, or model 2. The last one is most common to use model 2 with cyclic structures. So we'll just place the OH group at the more substituted carbon here. We just want to make sure that we draw the anti. All right, moving on to our next reaction, which is anti-dihydroxylation. So dihydroxylation is the addition of two hydroxyl groups, also known as OH groups or alcohol groups, across the pi bond. So ethylene will end up getting converted to what is called a diol through this process, the dihydroxylation process, which produces ethylene glycol, which you know is antifreeze. Okay, so anti-dihydroxylation of an alkene is a two-reaction process. We start by treating an alkene with what's called a peroxy acid. That will form an epoxide. This is reactive, but it's isolatable. You can isolate an epoxide. It's stable enough. You can take an NMR of it, for example. And then we can treat that under acidic conditions, like dilute sulfuric acid, and we will end up with the anti-dihydroxylated product, right? Or you can think of it as trans. Remember, anti and trans are not exactly the same thing, but sometimes the terminology is used to mean the same thing. And because this is not a chiral product, or sorry, is a chiral product, it's not a meso compound, we will get the enantiomer as well. Let's take a look at this two-step process, one step at a time. So remember, the first step in the anti-dihydroxylation process is conversion of the alkene to an epoxide. This is actually a one-step reaction where you can see a lot of electrons are moving around simultaneously to go directly from the alkene to the epoxide intermediate. And the byproduct is a carboxylic acid. You start off with this peroxy acid, which contains an oxygen-oxygen bond, which is a very weak bond. So nucleophilic attack on this oxygen will cause loss of a leaving group. These electrons could be delivered to the oxygen as a lone pair, or you can just shift them over to form a pi bond. If I form a pi bond, then I need to move these pi electrons to avoid exceeding the octet on this carbon. I can shift these electrons up onto the oxygen to form a lone pair, or just move them directly to do proton transfer. So these electrons are picking up this proton, then the electrons are left behind to attack the positively charged carbon that's left behind when the pi bond does its initial nucleophilic attack. So all of these electrons are shifting simultaneously, going through a transition state, leading to the two products. Different peroxy acids can be used as the reagent. MCPBA, which stands for metachloroperoxybenzoic acid, is a common reagent because the byproduct is metachlorobenzoic acid, which precipitates from dichloromethane, which is a common solvent used in this reaction. And so it's really easy to remove the byproduct. You don't have to do an extraction to remove it. You can just filter the byproduct off. That's what makes it convenient. Okay, so the epoxide is then reacted with water and an acid catalyst to form the antidiol. So remember, this three-membered ring is reactive, and the oxygen is still basic. So when treated with an acid, it can pick up a proton. So this is a proton transfer step, now forming an even more reactive intermediate, because now this is a positively charged oxygen, which really wants these electrons in the carbon-oxygen bond so that it doesn't have to have as much positive charge, which leaves these two carbons more electrophilic than they were before. Which means that if they're really electrophilic, there's a huge driving force to break open the three-membered ring, because remember, three-membered rings are not stable, right? Plus, there's a huge electronic drive because of the positively charged oxygen. Even a weak nucleophile like water can do a nucleophilic attack on this highly electrophilic carbon. Because it's going through an SN2-like process, we're going to get inversion. So the two hydroxyl groups will end up on opposite sides, and we call that the anti-product. After deprotonation to form a neutral diol, we are done with the reaction. We have our anti-dihydroxylated product. At this point, we've seen three different key intermediates that have some similarities. We just saw the protonated epoxide. We've looked at a bromonium ion before, and we've looked at a mercurinium ion in the oxymercuration-demercuration reaction from earlier in this chapter. We want to note that these all involve three-membered rings where the atom attached is positively charged. These are highly electrophilic intermediates that are poised for nucleophilic attack at one of the two equivalent carbon atoms. The products will always be anti-products because the nucleophile must approach from the back, opposite the leaving group in an SN2-like process, and we'll end up with the anti-products. So if you remember the mechanisms, especially the key intermediates, like we just talked about the bromonium ion, the mercurinium ion, and the protonated epoxide. If you remember the mechanisms, it will help you remember the stereoselectivity. Right? You're like, oh, bromonium ion, anti, right? So those, as the more mechanistic knowledge you have, the easier it will be to remember the specifics of each reaction. Okay. Let's talk about syn dihydroxylation. We also have a process if we want the two hydroxyl group to be syn to each other. We can use either osmium tetroxide or potassium permanganate. Those will react in a very similar fashion to form a cyclic intermediate. In this case, it's called a cyclic osmate ester. And a reductive workup will cleave these oxygen osmium bonds and replace them with protons, and we'll end up with the syn dihydroxylated product. Osmium tetroxide is both expensive and toxic. And so commonly it is only used in a catalytic amount along with a co-oxidant such as NMO. And so if you see NMO, don't worry about it. Basically, it is oxidizing the byproduct back to osmium tetroxide. So osmium tetroxide reacts with the initial alkene forms a reduced product where the osmium is reduced. The NMO oxidizes it back up so that it can react again. So you only need a catalytic amount. So sometimes different co-oxidants will be mentioned and sometimes they won't. And a lot of times that will just depend on, in the lab, the scale of the reaction being used. For example, if I have 10 grams of cyclohexene that I need converted to the diol, then I would not want to use corresponding equivalent of this very expensive and toxic reagent. I'd only want to use a tiny bit and then use a co-oxidant. However, if I had 2 milligrams, then it might not make sense to add a co-oxidant because it would only take a teeny bit of osmium tetroxide anyway. So sometimes these co-oxidants will be mentioned and sometimes they won't, right? And just note that anytime you see osmium tetroxide, regardless of whatever else is mentioned on the arrow, sometimes they'll mention the reductive workup, sometimes they won't. You just want to think osmium tetroxide, syn dihydroxylation. That will get you where you need to go. Syn dihydroxylation can also be achieved with potassium permanganate, but only under very cold temperatures because potassium permanganate is a strong oxidizing agent that can oxidize alcohols further to form other products, which would be undesired if this was our desired product. So it has some limitations, but kept very cold, sometimes it can be successful and it's a lot cheaper than osmium tetroxide. So you can see that it has a very similar structure on this side, right? Where the metal has 2 double bonds to oxygen, can form that same type of cyclic intermediate, which can eventually be reductively cleaved to form the syn diol. Okay, let's go ahead and predict the major products here. So in one case, I've given conditions that form anti-dihydroxylation products. And in the other case, we have conditions that form the syn dihydroxylated product. So we're practicing both reactions simultaneously. And remember, with cyclic substrates, it's common to use model 2 to draw the products. And this substrate will only end up with 1 chiral center. So it actually won't matter which set of reagents, you'll get the same products. And then this is going to be the case where you're going to form 2 stereocenters, and we'll want to make sure to use both models to draw the products in both reactions, and the products will be different. Because remember, one is anti-selective and one is syn-selective. All right, go ahead and do your best to predict the products. Don't forget to write plus an enantiomer when one exists. But don't just write that on everything, because if the compound isn't chiral, right, and you write plus an enantiomer, that would not make sense. All right, I'm going to assume that you have practiced these. If not, go ahead and pause it before we start talking about it. And let's go ahead and start working on these. So again, we want to remember, right, which conditions do which. So this gives you the anti-dihydroxylation products, right? And then these down here, you want to remember will give us syn dihydroxylation products. Okay, so based on that, we can work on trying to draw the products. So we have 5-membered ring. Right, I'm going to use model 2, so I'm going to keep the ring in the plane. And then I want to make sure that my 2 hydroxyl groups that I'm adding get added anti. So if I place one on a wedge on one carbon, then I'm going to place the other one on a dash. Right? And the enantiomer can also form, of course. And over here, we get syn dihydroxylation. So again, our 5-member ring, I just want to draw the 2 groups on the same side. So either both on a wedge or both on a dash, and plus En. Okay, moving over here, remember I said that this does not become a chiral center when it gets a functional group because of the 2 hydrogens that are here. So the only one that becomes a chiral center is this one, in which case we're always going to get a racemic mixture, right? So we're going to get the same product regardless of which condition, because these are both dihydroxylation. They do give you different stereochemistry, but only when two chiral centers are formed. And in this case, only one is formed. Right? So either way, we would get the same product. Right, so same product because only one chiral center is being formed. All right, down here, we are going to form two chiral centers. So both of these will become chiral when the two hydroxyl groups get added. That's when we want to make sure to draw the correct relative stereochemistry. And we can do it through either model, right? Model 1 or model 2. So we'll do both, right? We'll say, how do we do it with model 1, right? How do we draw the product with model 2? All right, so we want to, with model 1, we're going to add the two groups in this relative orientation. Remember that we're adding two OH groups. And then we're going to draw in the products here, making sure that I only do anti products here and I do syn products in that case. So with anti, we end up switching to. So I can keep this side the same, and then I can switch this one. Okay, so this plus the enantiomer. Right, if I was doing syn, I started out the same way, right? But I don't switch anything. So this methyl, which is coming sort of forward, and it stays like this, and then the other methyl is on the same side. So these remain on the same side. Okay, with model 2, we'll start with keeping the longest carbon chain here in the plane. And then we want to make sure to add the OHs on dashes and wedges. Remember, anti is opposite, so we'll do OH up, and one OH should be going back. Right, and syn will be the same, so either both on a wedge or on a dash. Okay. Back to the slides. The last reaction we're going to talk about is ozonolysis. So this is also called oxidative cleavage because we're now actually doing a carbon-carbon bond breaking reaction. So this is kind of unique because previously we have not broken the carbon-carbon bonds. We just added two groups across the double bond. So this one is very, very unique. Initially, it's an addition reaction. And we'll look at the mechanism to see that. But eventually, the carbon-carbon bond between the two carbons actually breaks. And we end up with carbonyls on both carbons. So if a carbon has two R groups attached to it, it becomes a ketone. And if it has a hydrogen on one side and a carbon, it becomes an aldehyde. And if it had two hydrogens, then it would become formaldehyde. So the reagents for this ozonolysis or oxidative cleavage are ozone and followed by a reductive workup using DMS, which stands for dimethyl sulfide. Also, zinc can be added as the second step. So you may see zinc sometimes, zinc water instead of DMS. So let's talk about ozone. Ozone is O3, and it exists as a hybrid of two resonance contributors, right? Where both oxygens that are terminal are sharing a negative charge, and the oxygen in the middle has a positive charge. You can imagine it's pretty reactive. So ozone, right, will react with alkenes. So think about this oxygen with a positive charge. Remember, we've seen this before, like with the protonated epoxide. Whenever you have an oxygen with a positive charge, the neutral atom attached to it, which in the past was carbon, but in this case now is oxygen. That's the one that actually receives the nucleophilic attack. So the pi bond, which is nucleophilic, is actually going to attack the oxygen that's neutral so that the pi electrons can go to the central oxygen, leaving it to be neutral as well. That would leave a positive charge on the other side, which if it's next to a negatively charged oxygen, should cause a reaction, which will form a ring in this case. So we form what's called the initial or first ozonide intermediate. That is not stable. Look at these oxygen-oxygen bonds. Those are, are not stable. So it's not going to stay this way. This is just an intermediate. What is stable are carbon-oxygen double bonds, right? Carbon-oxygen double bonds are very, very stable. So there's a driving force to form them as a result. So if we use one of these lone pairs on the oxygen, push electrons to form a pi bond, then we've generated that carbon-oxygen double bond. But because we cannot exceed the octet on this carbon, there'll be electrons that have to be simultaneously leaving this carbon if it's going to accept a pair of electrons from the oxygen. So that can break this carbon-carbon bond. Those electrons can flow to form another carbon-oxygen double bond, so another strong bond, breaking a weak oxygen-oxygen bond in the process. So it actually, after forming a ring, breaks open into two pieces again, or two separate molecules. Now, the negatively charged oxygen will be attracted to the positively charged carbon. It's positively charged through induction and also through resonance. And then the electrons, which could go up to the oxygen as a lone pair, making it negatively charged, can also then be used to do nucleophilic attack on this positively charged oxygen, or carbon. Remember that this one is electrophilic because it's double bonded to an atom that is positively charged. So it can accept electrons through nucleophilic attack. The pi bond will go to satisfy the atom, the positive charge, neutralizing it. This gives us our second ozonide intermediate. This one is a little bit more stable than the first one because we have less weak bonds. Right now we have more strong carbon-oxygen bonds and less oxygen-oxygen bonds. But it's still not completely stable because it still has this very reactive bond. So a mild reducing agent can come in, do a nucleophilic attack. We can break these open to reform carbon-oxygen double bonds. And then these electrons go on to the oxygen. So one of these oxygens essentially gets transferred to the reducing agent. So dimethyl sulfide will get converted to dimethyl sulfoxide, which is also DMSO. It's an organic solvent. And we'll end up with two carbonyls where the carbon-carbon double bond was previously, where both carbons get oxidized to carbonyls. And so this is, really synthetically useful because there aren't too many reactions that can break a carbon-carbon double bond, but ozonolysis can do that. So let's do some practice. Let's determine the organic reactant that was used to form the product below via the ozonolysis reaction. So see if you can work out how to go back to the reactant, and then we'll talk about it. Okay, so it's actually not too difficult typically to go back to the reactant, because what we want to do is identify those carbonyl carbons and then use them to reform a carbon-carbon double bond. In this case, if this carbon is attached to this carbon with a carbon-carbon double bond, or as an alkene, then this would have been a ring, right? This would be a 1, 2, 3, 4, 5-member ring. So I can go ahead and draw a 5-member ring. Okay, and you can label the carbons. 1, 2, 3, 4, 5, where 1 and 5 were previously attached. And attached to 1 is also a methyl. So we'll go ahead and add that carbon. I didn't number it because it's not part of my ring, but I just want to make sure that it gets added later on. And 5 has a hydrogen attached. not need to draw. So if we were to cleave this through ozonolysis, then we would end up with this product. All right, so the last slide is just a summary slide of all of the different reactions that were covered in this chapter. Recall we're doing alkene addition reactions. We're adding different groups across the double bond. So you want to think about when you're looking at these reagents, what's getting added across the double bond? And in this case, with ozonolysis, it's 2 oxygens that eventually leads to breaking of the carbon-carbon double bond and carbonyls. But in other cases, this carbon-carbon bond remains intact, and we add 2 groups across the pi bond. Ask yourself, is it the same group or different groups? If it's the same group, we don't have to worry about regioselectivity, like 2 bromines or 2 chlorines, 2 hydrogens, 2 OH groups, that sort of thing. But sometimes it's 2 different groups. Maybe you're adding a halogen and a hydrogen, right? Or an OH group and a hydrogen, or an OH group and a bromine, right? There's a lot of different possibilities where it's 2 different groups. In that case, you want to ask yourself, what's the regioselectivity? Sometimes we can summarize that with Markovnikov versus anti-Markovnikov rule. Or in the case of the halohydrin reaction, we just want to remember the OH group gets added to the more substituted carbon. And then ask yourself, how many stereocenters are being formed? If there is 0, then you don't need to worry about stereoselectivity. If there's 1, it's always a racemic mixture. And if there's 2, ask yourself, is this reaction anti-selective, syn-selective, or neither? If it's neither, then you actually get both anti and syn products. So you could get potentially a mixture of 4 stereoisomers if we're forming 2 new stereocenters. Based on the 2 to the n formula, where n equals 2, 2 to the 2 would be 4. So you could get as many as 4 products in a reaction that is not syn or anti-selective and gives both, and is forming 2 stereocenters. So there's lots of different ways this can be, needs to be practiced. What about ring structures? What about, so those cyclic structures versus acyclic structures? Which model do I want to use? Model A, model 1, or model 2 for drawing products? Do I even need to use a model because I'm not even forming stereocenters? Those are all questions and things that you need to practice. There's great practice with the activities, and as well, there's many problems in your book that I encourage you guys to practice with.